Good morning, good afternoon, wherever you are on this planet, and welcome to our SETI Live. Today, we are going to have a very special SETI Live about this mysterious and intriguing object called Oumuamua, the celestial messenger, the interstellar object, whatever you want to call it. And to have this conversation, we invited renowned scientists at the SETI Institute, Matija Ćuk. Hi, Matija, how are you?
I'm good. Hi, Frank.
Hi. So Matija is a theorist. That's the way I can describe you the best, right?
Yes, and proud of it.
So I'm an observer. Matija is a theorist. We do talk to each other from time to time in the hallway, but that's all. No, I'm just kidding. So Matija is a theorist who specializes in the determination of orbit, characterization of orbit for formation of planetary system. He has numerous papers on the formation of and the origin of the moon, for instance. You may have seen them published in Science the past 5 years. So Matija, we invited you today to talk about Oumuamua because it's a topic of conversation that we hear a lot at the moment. People talk about it in airplanes, in train, at dinner parties, and also in the scientific community. So first of all, I just would like to mention people that we are going to have a short conversation of approximately 15-20 minutes, and we hope to have your questions and to be able to answer to all your questions. So don't hesitate to write your questions while we are talking here about, first of all, please, Matija, tell us what is really Oumuamua for you.
So Oumuamua was the first interstellar object that went through the solar system. It was detected in the fall of 2017. And now we know of two interstellar objects. The comet Borisov also came through later. Oumuamua was, apart from being the first such object, we expected to see it sooner or later, but it was different from what we expected. We expected a comet, and later comet Borisov turned out to be your average comet, mostly. But Oumuamua was much smaller than what people expected. It had a very elongated shape, more elongated than most asteroids and comets. For a long time, we couldn't see any cometary activity. Actually, we never saw any cometary activity. It was only indirectly induced when we noticed that something is pushing it along its orbit. And also it was tumbling, which was hard to explain until this push was detected, which kind of goes together with tumbling. So altogether, it was very different from what we expected. So that launched 1,000 theories about how we got Oumuamua.
Yeah, we had a SETI talk shortly after the first publication of papers on this topic, where you describe some of your work on the origin and the characterization of Oumuamua. Can you tell us a bit about your involvement in this research, more precisely?
Yeah, so while Oumuamua was still being observed in the winter of 2017-2018, there was no indication of cometary activity. And as I said, only later, when people realized that something is pushing it around, and for comets, that's pretty much always outgassing, that gas coming off like a rocket effect of the surface of the comet. But it was detected later, only when its trajectory was analyzed. At that time, there was no indication of cometary activity, which was really puzzling. Plus, the puzzling nature of its small size is just the mathematics of how many bigger comets versus smaller comets we have kind of work that it's easier to see 1 kilometer comets as kind of a sweet spot. Nobody expected the first object to be without a comma and to be only 100 meters across or so, as Oumuamua is. We don't actually know how big it is because we didn't detect thermal. So we only know how bright it is, and therefore, depending on how reflective it is, it can be a bunch of sizes, but probably around 100 meters. So I proposed at the time that you can get a bunch of dry rocks of that size by destroying a planet, a super Earth planet, like many exosolar planets are, in a close encounter with a red dwarf star. So since then, we don't need dry rocks. So that kind of made Oumuamua a little bit less weird, that it's probably a comet, and therefore you can use cometary material, but it's still a weird kind of comet. We didn't see the activity. Now, that basically means that it could still be ice there that is sublimating, but it's really short of dust. So I still think that something like the extraction of a larger body, anything from a planet to planetesimal, by tidal field could be an answer, except that probably we don't need something as dense as red dwarf stars. Lots of extrasolar planets would do. As Jupiter destroyed Shoemaker-Levy 9 in a close passage, because as comets come close to planets, tides can pull them apart. And if you have a super Jupiter planet, many times more massive, tides will be many times stronger. So that might be part of the answer still. But we need to know more about these kind of bodies, and we hope we'll see more soon.
So in short, we discovered in 2017 this interesting body. We follow up its orbit, its brightness. We saw that it was we saw that the brightness was varying a lot and varying in a very weird way. So we then make a suggestion that it's a tumbling, elongated body. We saw slight deviation due to outgassing probably, but we never saw a coma on this body.
That's
and
right.
Your hypothesis is that this body is a fragment of a planet or that's been disrupted coming from another planetary system.
Yeah, I'm not the only one who's proposing tidal disruption. Some people, like Sean Raymond of Bordeaux, they want to break up comets into smaller comets. And that works also in our own solar system. Jupiter disrupts some fraternal comets. Oumuamua is so dust-free and so elongated that maybe a more radical explanation is needed, in which case it might be useful to use the tidal fields of planets that we don't have in our solar system. Not every solar system is the same. And that can answer the question of how come there are so many of them. We assume there are so many of them just because the chance of seeing one is relatively low compared to a real comet, like comet Borisov, which is bigger and brighter and has a coma, much easier to notice. So that just means that if Oumuamua is a standard object of that type, there must be 10 to the 15 per every star in the galaxy, which is a lot. That's a million billion. And you just have to make them that size, because if in our solar system, there aren't that many small bodies being ejected, because most of the mass is in bigger comets, just the way small bodies are distributed.
Yeah, so if we take into account the fact that we have seen so many different planetary systems around us, we can assume that this comet or this interplanetary body is different because it's coming from a planetary system which is very different. Planetary system that could have, for instance, or had in the past, a gas giant very close to its sun or something like this. And that's a very important point, is that we learn a lot about planetary system formation, and you're very like one of the key person at the SETI Institute in this field. So you do know that there is different planetary systems and different kind of dynamic in those planetary systems. So the origin of this body, which is weird, it's true that it's a weird body, could be then one of these different planetary systems. Is that a right summary?
Yeah. The crucial question is, when you have one body like this, which of its properties are just random, like one of a kind, and which are systematic? So it's elongated, it's dust-free apparently, or has very little dust, and it has a small size, that it's a characteristic size of 100 meters. So maybe it's just a fluke that we got a body of that size. Maybe it's a fluke that we got an elongated body. So unless we see a couple of them, or a good sample, we don't know which properties are characteristic of this population, if it is a separate population, and which are just luck of the draw.
Okay, so that's the end of our SETI Live then. No?
I think there is more to it.
There is more to it? Okay, well, tell us. The reason we're talking about that today, it's because, as I mentioned, people are talking about this body everywhere in the news because something happened. Someone wrote a book, and
right.
You luckily read this book. Can you show it?
Yep.
Tell us a bit more about this.
So it's Interstellar. Oh, my background is messing up.
It's okay. What's the title again?
Interstellar by Avi Loeb, who's
Okay.
a professor at Harvard University. And the book is about many other things, but yes, at its core, it proposes that Oumuamua is likely a artificial body, an alien artifact. And the book forcefully makes a argument that this is the best, the superior hypothesis in explaining Oumuamua, which is kind of at odds with the majority opinion in the scientific community.
And apparently this interest also reached our social media. We have more than 200 people watching us now, even more. From Paraguay, from Rhode Island, from the Philippines, from Illinois, from Germany, still awake, from Holland, from West Virginia, from Brazil. So there is people around the world who are interested to hear about Oumuamua and what you think about its origin or its true nature. So let's go through some of the hypotheses of the book and maybe tell us a bit your thoughts on that. The shape, it's something that really kind of puzzled people when we saw the first light curve. I do remember when we saw the first light curve, I thought personally that it was a binary asteroid because, you know, binary asteroids have this extremely high amplitude light curve when we get the first one. And I thought that what we're seeing is basically two bodies orbiting around each other, and the drop in the magnitude was due to the fact that we could see one for a few hours and then two of them separated. But it's not the case. So there is two hypotheses at the moment. There is the pancake or the cigar. So tell us a bit what you learned or what you knew already and what you learned from this book.
Yeah, so the book makes like two groups of arguments. One is about discussing the natural explanations, which are dominant in the scientific community, and then presenting arguments for the extraterrestrial hypothesis. So I was not really happy how the arguments for like the mainstream arguments were presented, and this cigar versus pancake question is case in point. So everybody has seen this picture of a space cigar that represents Oumuamua, and the fact is Oumuamua is 10 times brighter in some orientations as it tumbles around than in others, which means that it's either a very elongated body or a very flat body. So when you see it side on, it's you see much less of it than you see from the top. And everybody would tell you who's serious about it that we don't really know which one it is from the data that we have. Mm-hmm. People have tried analyzing data, and what kind of is extra in the whole calculation is the torque on the rotation, because if there is a jet coming off Oumuamua that's changing its orbit, it has to change its spin. So can all these things work together? Like, and you know, what do you get when you try modeling the jet and the spin and the light curve and so on? So the book claims that there is 91% chance that it's pancake rather than a cigar, and it goes back to a paper by Sergei Mashenko in Monthly Notices, and I look at the paper. That's not exactly what the paper says, although the paper does advocate pancake. And apart from the geometric arguments, which would favor pancake in some cases, there are also dynamical arguments. You know, to have a pancake give you a light curve, you need to spin it around one of the long axes, and that bodies don't like to do that long term. And then there's also the photometric arguments. That means that just because you're seeing 10 times drop in brightness doesn't mean that you're actually seeing 10 times less of the body, because you know, some place, depending on the angle at which you're seeing a surface, you can get a different amount of reflection. So it's more complicated than that. So I would say that saying that it's definitely a pancake and not a cigar is just not something that's justified by data.
Yeah. So this is important to remind people that we did not see the shape. Okay, we assume the shape from the brightness variation, and this paper from Sergei Matjenko basically analyzed two types of shape and suggests that the pancake is a possible shape compared to the cigar, but they don't say that the pancake is the most likely shape. That's not really what this paper is about. We have people joining us from everywhere in the world. We have someone from Serbia who say, Pozdrav iz Raske Matija Ćuk.
Ah, excellent.
We have people from Portugal, from the UKs, from Romania. And we also have donations. We have a donation by Jonas in Sweden. Thank you very much for your donation. And please, let's continue this conversation before I keep track. I lose track of what we have to talk about. So there is also this idea of the lack of activity. That's something that surprised us. You mentioned that we were expecting to see a comet if a comet coming from the outer part of the solar system, another planetary system, after crossing the cold space for millions of years, I'm making numbers, we will expect this comet to light on by coming close to the sun because of the heat coming from the sun. So what's the story here? What happened?
Well, so I'm a theorist, unlike you, but like Professor Loeb, and I didn't quite appreciate before all of this the complexity of comets and how every comet is different, like every child is different. So what we mostly see when we see coma is dust. So it's particles about micron sized, and they're really good at scattering light. And some gases can be seen also using spectroscopy, but mostly most of the mass that comes off the comet might be gas that is invisible. So the coma that is visible and the jet that's changing the orbit are not necessarily physically the same thing. Mm-hmm. They're correlated in comets. Now, of course, there is some scatter of how they're correlated. Some comets have more dust, some have more gas compared to dust, but there is no reason why a body coming from a different solar system has to be exactly the same if it was formed under somewhat different circumstance. So saying that it's physically impossible, pretty much as the book does, that there is enough jet outgassing so the jet can move Oumuamua along its trajectory, it's not physically impossible. It's just that if Oumuamua was like an average comet in our solar system, we should have seen the coma for that amount of outgassing that we see from the reaction on the orbit. But it's not from our solar system. So I think it's really jumping the gun to say that outgassing is not a good explanation. Of course, it's just a hypothesis, as we haven't seen the coma. But that's one place where actually my intuition was wrong compared to the comet observers. They kept not seeing the coma, and then I decided that, well, this tells us something. Maybe you should think about it not having coma at all. But people kept saying, oh, let's wait for the trajectory to see if they see something. And I was like, what are they talking about? Like, you can't see coma, you're not going to see anything. Turns out there is a back reaction on the comet. So yeah, comets are weird, and you have to have open mind, especially if this is something different from what we usually have in our solar system. So I think both the cigar shape and the back reaction from outgassing of gas onto the from Oumuamua are not only viable, but maybe the best explanations that we have so far for its trajectory and shape.
Yes, so it's once again the problem of using the physics of what we study in our solar system and applying that to another planetary system, assuming that we're gonna see the same rate of outgassing versus dust. It may not apply for a body which is very different, coming from a different environment, but also a body which form in a different place. Maybe the composition is different in this other planetary system. Maybe there is less rocks or more ice or vice versa. And that's a very important point. That was the first body we discovered like that. The second one, Borisov, seems to be more similar to what we expect from a comet from our own solar system.
That's right. And one other thing about the shape, a reason why most people assume that it's elongated is just that asteroids and comets are usually elongated and not pancake shaped, usually. However, since then, we've seen Kuiper Belt object Arrokoth, which is made from two pancakes.
Yeah.
So we always learn something new from our other solar systems.
Yeah, and this discovery of I forgot his name, Arrokoth, happened very recently. I mean, we're talking about something that happened a year and a half ago.
That's right.
And that was a surprise for everybody. And I do remember first we have this two component, and then when you finally get the other data, we found that it was flat like a pancake, which was absolutely surprised everybody in the community. We have even more people joining us now from Norway, from Amelie in Germany, from France, bonjour, from New Jersey, from London. And we have donation coming from Danny. Thank you very much for your donation, Danny, and thank you for following us on Facebook at the moment. Let's talk about the extraterrestrial explanation, the hypothesis that is described in the book at length, I'm assuming. There is this story of the origin of Oumuamua from the orbit. The author and other people calculated that Oumuamua will come from what we call the local standard of rest. Maybe we should explain that first and then explain why this is important.
Yeah, so Sun orbits the center of the galaxy together a bunch of other stars, and every star has a slightly different orbit, but most stars in their neighborhood orbit kind of together as a set. And then you can take an average of their velocity and determine kind of an average motion by which the whole section of the galaxy is moving, and that's the local standard of rest. And then if some star is passing by really fast, you can kind of refer its velocity to the local standard of rest. So the fact that Oumuamua is close to local standard of rest by itself is not strange. It just means it comes from a star that might not be too far away from us. But what was kind of surprising is how close it is to the local standard of rest. Just statistically, you're unlikely to hit bullseye if you're playing with its how to say the vectors. Like it's basically the same as bullseye in 3 dimensions, and it's really close to the local standard of rest. If it got a bunch of random kicks from a random star that has its own velocity relative to the standard of rest. So Professor Loeb explains that by having the Oumuamua be some kind of buoy that floats in space. Then switches to some other explanation, but I really don't think it's a very good explanation, because then you still need large numbers of these bodies. And it's also, while the book gives good analogies for why would somebody send a solar sail probe to another solar system, I'm not willing to believe in space buoys more so than interstellar comets, even without dust and with strange shapes. And also, extraterrestrial explanation by itself is not end all. We can say, okay, it's artificial, but what does it actually explain? Buoy would explain its velocity relative to local standard of rest and nothing else. While on the other hand, a probe would explain why it's here, and we don't need 10 to the 15 of them per star because it's targeted somewhat. But then other things don't match the probe. It's too slow. Nobody would send a probe that slow that's basically not moving relative to the stars. It's also tumbling, so it's definitely not operational solar sail right now. Or you can say it was a debris, like left over from billions of years ago or something like that from an ancient civilization. You still need, as I said, 10 to the 15 of them per star. That's much less mass because they are just thin foils than you would have from so many asteroids or comets. But it requires shredding, let's say, million Dyson spheres worth of surface area, just to give you a comparison. So it's also kind of a big claim, and evidence is pretty thin.
What I'm getting from your explanation and the discussion we had a few days ago, and from reading some of the article, is that even if if we assume that it's an extraterrestrial artifact, it does not explain anything. It doesn't explain the tumbling. It doesn't explain the presence. What's what this artifact is made of, or what is true nature, and also what this extraterrestrial species who send this or let that here want to do with it. We have no idea. I mean, it would be great if the extraterrestrial explanation will give us indication of the kind of tick the list. The tumbling is due to that. The color is due to this. The presence of that, but it's not the case. In fact,
no single extraterrestrial explanation actually explains anything more than a simple natural one does. It's exactly. Only in the book, it's kind of, you jump so fast from one to the other that it's not super clear that actually these explanations are mutually exclusive in a way.
Thank you. One thing I want to basically briefly mention is not in the book, because I don't think he mentioned it in the book. Maybe you remind me this. Does he talk about Borisov, and what can you tell us about
the book does mention Borisov, yeah.
Yeah.
Well, it makes a contrast between the two, because Borisov is a standard comet, more or less. There might be some difference in the chemistry, while Oumuamua is nothing like standard comets, so that's argument more than Oumuamua is something different. But all it means that there might be two classes, and with two bodies, defining two classes is a little bit rich. But there might be two classes of interstellar objects, and maybe when we get a third, maybe there's more than two. But saying that this other class cannot be natural is not really a strongly supported claim at this point.
All right, thank you. We already have been talking for almost half hour. I have a question from you. What should we have done to really understand the nature of Oumuamua? What is missing in all the measurement we did? What if we had an infinite amount of money right now and you could go back in time? What would you have done?
I'm a theorist, so that's a question for observers. I did ask observers that, and at the edges there are a few things you could do, but I think people are more focused on the future. That the amount of data we got on Oumuamua is probably going to be eclipsed by the data we're going to get on the next few objects.
Because we're ready.
Yeah, now people are definitely more ready.
Because I think something people don't realize that this Oumuamua took us very by surprise. I mean, I do remember when I heard about it the first time, we didn't think about acting quickly, and we did discover it very late. In fact, it was already well inside the solar system. It's not the case for Borisov, so we have more observations. We have follow-up with multiple instruments. We didn't have that for Oumuamua. But there is this interesting mission called the Comet Interceptor. Maybe you can mention that briefly. I know you're a theorist, but come on, you do know about it.
Yeah, well, I mean, we can always. I mean, it all depends on the amount of resources you have put into it. If something is really interesting, you can send a spacecraft after it and catch up. But we have to be careful. I'm talking as a theorist, that you send a spacecraft after one, and then before it gets there, another nicer one passes by, and you wish you send it after the other. So let's see what's out there before we throw big money after it.
Yeah. So the Comet Interceptor is a mission funded by an ESA. It's going to be basically a mission ready to explore a comet that's going to pass nearby us, and we don't have yet the target for this mission. I think it's one of the first time we do something like this. We developed a mission before having the target, and the mission will stay in the Lagrange point and be able to go toward a comet or an interesting body like an interstellar body to explore it. And there will be typically what you expect on the mission, a spacecraft dedicated to observe a comet. There will be, of course, a camera, visible infrared, spectrograph visible infrared, dust particle analyzers to kind of capture the dust, a plasma analyzer to be able to understand the surrounding, the magnetic field and the interaction with the magnetic field. It's a mission with a JAXA component as well, the Japanese Space Agency. So when this will be ready, when we have another interstellar body, I think that will be the mission that will explore it and send us pictures of it. Okay. Before the conclusion, let's take a few questions from the people watching us at the moment. So we talk about the shape already, so I'm not going to take any questions about the shape. Yeah, a very interesting question here we have. Is Oumuamua exciting for astronomers, even if it's not a probe sent by aliens?
Yes, so that's where I differ from Professor Loeb. I think in the same forum a few weeks ago, he said, maybe it's a rock, so nobody cares. Well, Frank cares, and I care. So it's from a different solar system. So if it's a piece of rock or ice, it's still wonderful. When I was a kid, we didn't know of any extrasolar planets. Now, not only we have them, we have interstellar objects. It's just amazing.
Yeah, I think that's something important to mention, is that we learn a lot by studying the small solar system bodies in our own solar system. That's why we send missions to explore asteroids and comets. Those missions cost money and takes a lot of time to develop, but they gave us a lot of information on the formation of solar system bodies. Understanding how we form planets is key, for instance, to really understand the true nature of our solar system. So we know we cannot go to another planetary system yet. So having them coming to us and observing them and understanding them the same way will give us a lot of information about those other planetary systems. And I think it's a fascinating, Oumuamua is a fascinating object because it's coming probably from another planetary system, but just the fact that we can study this and get information about the shape and maybe in the future for the composition of the next one, we will get a lot of constraint of how we form other planetary systems. I have another questions here. How do we know that Oumuamua is an interstellar object?
It's a very good question. So it goes much faster than anything in our solar system. We saw it only on the way out. So if we assume it's a natural object, in which case its non-gravitational acceleration is small compared to its gravitational motion, then we are sure it's interstellar object. There's just no way it could have come from our solar system. Nobody could give it such a large kick. Even if it comes from, there was a suggestion it comes from Planet 9 or something like that in the Oort cloud, but actually it doesn't work out in terms of orbital dynamics, that no planet can actually give it such a kick. And it didn't come anywhere close to Jupiter either. So it definitely has to come from the other solar system. Of course, if it's an extraterrestrial artifact, we know nothing about it. We cannot assume much about its trajectory before we saw it. So that's a caveat. But otherwise, it's definitely interstellar.
So I have a question here. What have given the push or the momentum of Oumuamua to escape its planetary system? What kind of scenario you have? You mentioned that, but maybe you can elaborate a bit about this.
Yeah, so that's a part that's not unexpected, that solar systems should shed comets. Jupiter likely ejected, trillions of comets from our solar system. So when a small body encounters a giant planet, its relative velocity gets moved around. So basically, if you are on a bound orbit, that's elliptical orbit around the sun, you encounter a giant planet, come very close to it, you can get a kick that puts you on an open trajectory, hyperbolic, that goes away. And that's what happened to Voyager spacecraft that has been used artificially to fly spacecraft by Jupiter, so they will get extra kick and go on a faster trajectories to outer planets, out to Neptune. And then both Voyagers and New Horizon spacecraft are on interstellar trajectories. They've been kicked out of the solar system by Jupiter. We did it on purpose, so they would fly by outer planets on the way out. But now they are on a pretty much ballistic trajectory out of the solar system, just like many natural comets have in the past. As I said, one of the theories I like, and many other people have proposed, is that while passing by the giant planet, the body might have been broken up to shreds due to tidal forces. And so those two kind of go together. You just have to figure out the math, what is likely and what is physically possible.
So I think in the book, they mention something that you may want to answer. In the book, it's mentioned that so to escape the solar system, if you, for instance, you're a comet located in the old clouds of your planetary system, you need a push of like 1 or 2 kilometers per second.
Yep.
But now, if we consider the fact that this body is coming from the LSR, the push is calculated, I did not check that calculation, is 7,000 kilometers per second. So that's an indication, based on the author, that this body is artificial because it's been pushed by strongly. It's not a kick. It's seriously an impulse. So what do you answer to this?
What the velocities that comets have at infinity. So when they're really out of the solar system. So when they fly past Jupiter, they're kicked out at large velocity, just like the spacecraft were, like New Horizons. As they move away from the sun, they slow down. So actually, quite a few of the comets that are ejected remember the velocity of the sun around the galaxy, because once they get out of the solar system, they don't have much velocity left. You just need to kick them out. You don't have to kick them out fast for them to escape. So then you have two vectors that are completely independent in a sense. That's how the SAR was moving relative to the local standard of rest and how the comet was ejected. So for those two to kind of cancel out, it's unlikely. But I don't think that anything really tells you that it's artificial. It's just it just could be a fluke, and without a good explanation of why it is that, so we have to stick with the fluke. For example, when you have some kind of medium that affects drag on the orbit, you can say that it slowed down. But interstellar medium is very rarefied. Nothing is going to really slow down and stop relative to the standard of rest. So kind of just the randomness is the only explanation that really works.
Okay, we have a lot of questions on the color of Oumuamua and the spectroscopy of Oumuamua. You're a theorist. I don't know if you want to address that.
Yeah, so they didn't really see anything much except that it's red and doesn't have any strong features. Could be anything. Comets are red. Also some iron compounds are red. It's really not clear with which one it is. Now, since we've seen outgassing, probably has to do with with some kind of icy compounds. All it tells you is that it's probably not super clean, say, water ice, but beyond that, it doesn't carry much information. One thing I like to mention, because it's related, is its brightness. The book makes a big deal out of it not being very dark, because the first estimate was that it has a reflectance of 4%. Some comets do, and some asteroids are also very, very dark. However, we know enough in terms of its heat signature that it cannot be that big. It has to be smaller and therefore brighter. So brightness is at least reflectance is at least 10%. That does not mean it's in any way not a comet or an asteroid. Most asteroids, well, many asteroids have brighter surfaces. The regular S-type asteroids that we encounter every day. And then in the Kuiper belt, bodies are not that dark. First, we thought they will be as dark as some comets are. Arrokoth, for example, has a reflectance of 20%. So it's really a kind of a red herring to say that that it has to be shiny. It's not shiny. It's just not super dark.
Yeah. Okay, so I have questions. I'm going to answer to one of them about the orbit, because I have the calculation in front of me. I don't want to put you in a spot here. They ask, what's the brightness of Oumuamua at the moment? are we observing it at the moment? Well, Oumuamua is 22 AU from us at the moment, roughly. Its magnitude is 35. Typically, with a telescope, we can observe now magnitude 22, 23 at the best. So we are talking about a body here, which is way too faint for all telescopes we have on this planet. So we cannot observe Oumuamua anymore. It's too far away. It's a small body. Remember that a small body like that reflect the light of the sun. So the more distant it is from us, the fainter it will be, of course. So that's the reason we cannot observe and continue to observe Oumuamua, even get information about its location anymore. We just assume it's still drifting away from us, and after being close to the sun. One thing you mentioned, by the way, I don't know if you mentioned that a few minutes ago, but now when Oumuamua passed nearby the sun, its orbit got affected, right?
Oumuamua, it got completely turned around. It was pretty much on a kind of a U-shaped trajectory, or V-shaped. It came back and it was almost sent back the way it came, but with extra kick.
So he's not a buoy stable anymore. He's not in the LSR. He has a completely different orbit.
Yeah, so this was extreme example of an encounter, because it came within quarter astronomical unit of the sun. So it got really big kick. But if you leave it out there, stars are going to come by and kick it around anyway. So that it was in the local standard of rest when we encountered it is, I don't think it means anything.
Okay, so we have a lot of other questions, and we have to stop this very soon. But I do recommend you write your questions in the question on YouTube or Facebook, and we will take the time to answer to some of them. I also remind you, we had a SETI talk last year or 2 years ago on Oumuamua, where you're going to learn a lot about the color and the shape of this interstellar body. One question, it's a fun one, Matija, so feel free to say you don't want to answer to that. So do you believe that extraterrestrial life exists? Yourself, your personal point of view.
I don't know. I would like it to exist. Unlike Professor Loeb says in his book, I do love science fiction, and I, always thought about aliens quite a bit, and I would love to get some aliens here or anywhere. And I think it's possibly it exists, but it's our job to find it rather than to just guess if it's out there or not. And one thing I would like to say about Oumuamua is that the bunch of people who worked on Oumuamua, mostly observers, have written kind of a review paper after all the data was in, because our talk at SETI was kind of halfway through the whole thing. It was called Natural History of Oumuamua. It came out in Nature Astronomy, but it's fortunately available for free on arXiv, so you can read the PDF. It's a bit dense in the sense that there's lots of facts and figures and so on, but anything you want to know about Oumuamua, I wouldn't say everything you want to know. We want to know more, but everything we do know is there, pretty much.
It's there. And we will put the link on the description of this video so you can have access to this scientific paper. The question was addressed to me as well. So I'm going to say that in my case, I am convinced that there is extraterrestrial life in this galaxy, because there is so many worlds, so many potentially habitable planets, that it will be a waste of space, of course, that you have other life. And that's not coming from me, that's coming from Carl Sagan. So it's a personal belief. And that's not scientific. It's what I believe myself. And as we'll go back to Matija comments, our job at the SETI Institute is to find this proof of life. It's not to speculate about it or to assume it exists and then to make the research. We are searching for this intelligent life or even microbiological life at the SETI Institute. So thank you very much, Matija, for your time and for participating to this SETI Live. I hope we're going to invite you again to talk about some of the theory you have, one of those crazy theories you have to form moons and stuff like that in the future. Are you working on something interesting right now?
Oh, just I've been working on Arrokoth lately, so you'll be hearing about that. The pancakes in space.
Thank you. So thank you very much to all of our viewers for watching this. Thank you to the SETI Institute for helping making this happen. Lee, Rebecca, Bess, Barbara, and everybody else behind the scene here. Please join us, subscribe, share this video, like this video, click on the bell. You know the drill. Retweet. Help us to reach more people. We are a non-profit organization, and the contribution we have from your donation make this research possible. So join us, follow us, join our SETI Life. Next week, we're going to have another controversial topic on the the existence of life in the atmosphere of Venus, and some of the most recent analysis of data, which has been done by a researcher at the University of Washington. So join us, visit SETI.org, and see you